Well, welcome back to another lesson with Amanj. Well, today in this lesson, we're going to talk about those topics that are in the first section of grade 10's book. You know that the Ministry of Education this year, they actually changed the previous book, the old book, to a new one. So we are going to just follow the new book, the new curriculum, and study those topics that are over there. So in the first lesson, we have got some topics regarding to the sets of numbers. Well, in sets of numbers, we will mainly talk about like natural numbers, integers, whole numbers, rational, irrational, and finally real numbers. And we are going to mention non-real numbers too. Then we will talk about estimation of square root. Then we are going to come to properties of real number. Then finally we will talk about order of operations. Like for example, in a mathematical statement, if we have got like different operations, how are we going to deal with it? We cannot like randomly solve the question that it includes multiplication, division, power, bracket, and stuff. So there should be a rule, there should be something, an order to go and follow it to get the correct result. So here, in our first lesson that I already used this PowerPoint to solve the questions, to explain the lesson. Well, in the very beginning of our lesson, we are going to be familiar with this title, set of numbers. As I already said that we have different sets of numbers. The first one is natural numbers. So natural numbers start from like 1, 2, 3, 4, 5. In another term, we can call them counting numbers. All right. So according to our book, natural numbers start from 1. And then the second set that we have got is whole numbers. All right. So whole numbers, basically, they start from 0. So the only difference between these two is just number 0. So starting number for natural number is 1. The starting number for whole number is 0, and then goes on until positive infinity. And then the third set of number is integers. Well, integers are natural numbers, they're negatives, and 0. So basically, we can say that integers are positive numbers, negative numbers, and 0. But what I mean by numbers, like counting numbers, all right? For example, 1, 2, 3, 4, and goes to positive infinity. We have got 0 in the middle, and then we have their opposite, which is negative 1, negative 2, negative 3, and negative infinity. So there might be some cases that it's better to mention them for the integers. We said that counting numbers, right? But a number, let's mention some cases. Let's say square root of 16. Well, square root of 16, it's square root. You might say that, okay, since it's square root, so it can't be integer. No. Perfect square roots and perfect cube roots are also integer because they have got an exact root. So square root of 16 is equals to 4. All right, so since it's equals to 4, it can be an integer. All right. And another case, let's say 16 over 8. What kind of term is this? Excellent, fraction. So since it's fraction, you might say that again, so it's not included in the integers, because we said that just counting numbers, they're opposites, which is negative, they're negatives, and 0 as well. But it's a fraction. But this fraction, as you can see, the numerator is divisible by denominator. So 16 divided by 8 is equal to 2. And 2 is a member of integers. That's why take care of these kind of cases. Let's just give one cube root as well, a perfect cube root. Let's say cube root of 64. So cube root of 64 means a number, when you multiply 3 times by itself, it gives you 64. What kind of number is this? What number can be the answer of this one? Perfect, 4. I'm pretty sure you know this one. So because 4, if you times it 3 times by itself, you're going to get 64. Okay. Therefore, 4, it's an integer number. And then the cube root of 64 is also an integer number. So let's just come back to the lesson. and the rest of the types, sets. The most important one I can say, it's the rational numbers. So rational number, the definition of rational number is very simple. A number that can be written as a fraction like over A over B. So these A and B are real numbers when B should not be 0. Because if it is 0, it's going to be undefined. Alright? So it should be in this form, a form of a fraction, A over B. So the next one is irrational numbers. So irrational numbers, simply we can say that a number that it is not rational, it's going to become irrational. There are two types of irrational numbers. We are going to discuss about them. Alright, and then the final one, it's real numbers. So all these numbers are going to become real numbers. Like all the natural, all the whole number, all the integers, all the rational, and plus irrational numbers, they are all real numbers. Okay, and we have got non-real numbers. In the upcoming slides, we're going to talk about them. All right, let's just continue and see what we have here. Well, we have got some important notes that we need to take care of them in case if you are a grade 10 and even 11 and 12. So these are the basic notes. Okay, so the first one is all the natural numbers are rational. We should know this one. All the natural numbers are rational numbers. You might ask me, teacher, how? So, if we have a 3, positive 3, it's a natural number. For every single natural number, we have got a denominator of 1. Since we can write 3 as a fraction, so it's going to become a rational number as well. Okay. So the next note is all the whole numbers are rational. They have got the same story. For example, let's say the difference between natural and whole number was 0. So these 0 can have a denominator of 1. So as you can see, it's a fraction form. Since it's a fraction form, so it is a rational number. How about the next note? So all the integers are rational number. We have got the same story. For every single member of integers, we can have a denominator of 1. How about all the fractions? So fractions are the definition of rational number itself. All the fractions, proper and improper fractions, are all rational numbers. Okay, we have got two types of decimals that I already in my lessons with you guys, I mentioned it. So terminating decimals are always rational number. What kind of numbers are they? Terminating decimal, according to the name, when the decimal has ended, which means when we have got an ending digit. For instance, let me just maximize the size, okay, and change it to black. Imagine if you have 2, 6.6, 6, and this 6 is repeating. There are 3 dots here. So these 3 dots tell us that this decimal continues endlessly, but the decimal part is repeating. Whenever we have got this kind of cases, by the way, you can write this one, you can show it in this way as well, 2.6 and a bar line over this 6. So this line will tell us, it displays that this 6 is repeating. Okay, so all the repeatings are a member of rational numbers. So these are the notation of like sets of numbers. All right. Therefore, all the terminating It's like repeating. I am really sorry, guys. So I want you to just listen to me carefully. This is repeating decimal. So repeating decimal is a part of a rational number, and terminating is a decimal that it has got an ending digit. For instance, 6.5. So at 5, this decimal number has ended. Therefore, this is rational as well. So we have two types of decimals that they are rational numbers. First one is repeating, when the decimal part is repeating, and the second type is terminating decimal. For instance, 1.298. So there is no other digit after this 8. Therefore, this kind of decimal number is going to be rational number 2. guys. Okay, so all the naturals, all the whole numbers, integers, fractions, terminating and repeating decimals are all rational numbers. There is another case of rational number that we need to take care of them. It's all the perfect square roots and all the perfect cube roots. So let me just remind you about the perfect square roots. A square root is perfect that it came out of like multiplication of a number by itself. Like it's value of multiplication of a number by itself. Like how, for example, we are saying that square root of 1 is perfect. Why? Because it came from 1 times 1. Square root of 4 is perfect. Why? Because it came from 2 times 2. A multiplication of a number by itself. Okay? For instance, square root of 5 cannot be perfect. Why? Because we cannot find a number that if we multiply by itself, it gives us 5. Therefore, square root of 5 cannot be perfect. How about square root of 9? Yes, it is exactly 3 times 3. So you can just go and check them by yourself. For example, square root of 16, square root of 25, 36, 49, 64, 81, 100, 121, 144, and so on. They came from the multiplication of a number by itself. Okay, how about perfect cube roots? They are exactly 10 or 11. That's you need to know them, just like you know your names. Since they are few, so let's just mention all of them. Perfect cube roots. Perfect cube roots of 1. Again, it came from multiplication of a number 3 times by itself, because cube means 3. Okay, 1 times 1 times 1. So we are going to have 1. Therefore, cube root of 1, it's equals to 1. Cube root of 8, it's equals to 2. Why? Because if you multiply 2 3 times by itself, you are going to reach 8. Okay, how about cube root of next number, which is 27? Well, it's equal to 3 times 3 times 3. You are going to reach 27. Cube root of 64, it's equals to 4 times 4 times 4. So cube root of 64, it's 4. How about cube root of 125? So it's equal to 5. Cube root of 216, it's equal to 6. Cube root of 343, it's equal to 7. 7 times 7, 49. 49 times 7, 49, let's just check it. I'm not sure. 7 times 9, 63, 3, 6. 7 times 4, 28, plus 6, 34. Yes, cube root of 343, it's equal to 7. And cube root of 512, it's equals to 8. Which means if you multiply, if you times 8 3 times by itself, you are going to reach 8. I mean 512. And then find the last two that left. Our cube root of 729, it's equals to perfect 9. If you multiply 9 3 times by itself, you are going to get 729, because 9 times 9, 81. 81 times 9, it's equal to 729. And finally, the final one, the last one that you need to know it is cube root of 1000. It's equals to 10, because if you multiply 10 3 times by itself, you're going to get 1000. These are the perfect cube roots plus perfect square roots. They are all rational numbers. Okay, then we have irrational numbers, 2 types of them. Let me just make sure that the video is going on. Yes. Yes. Wait a second. I hope, guys, that you can see it clearly. Okay, irrational numbers, like 2 types of them are very important to know. So the first one, the first type of number that it is going to become irrational number is non-perfect square root and non-perfect cube roots are irrational. We said that the perfect ones are rational, the non-perfect one or imperfect one are irrational. What do you mean, Mr. by imperfect one? For example, let's come back to the explanation part and the pen. Well, the imperfect one, for example, square root of 2. It's imperfect square root. Why? Because you cannot find a number that if you multiply by itself, it gives you 2. Okay? So we cannot write this one as a fraction. So how about square root of 3, square root of 4? Be careful, it's perfect. How about square root of 5? Yes, it's imperfect, so it's going to be irrational. So it goes on. So between any two perfect square roots, there will be some other numbers. So the square root of them are going to be all irrational numbers. For example, between square root of 9 and square root of 16, there are square root of 10, square root of 11, square root of 12, 13, 14, and 15. They are all irrational numbers. Okay, so the perfect ones are clear. How about the cube roots? So cube root of 1 was perfect. So therefore, cube root of 2, it's imperfect. Cube root of 3, it's imperfect. Cube root of 4, it's imperfect. Be careful, guys. Cube root of 4, it's imperfect. Square root of 4, it's perfect. Okay? Because square root of 4 is like exact and it's equal to 2. But cube root of 4 has no exact result. Okay? The decimal part of it is endless and not repeating, which is the second reason, the second type of irrational number. So I hope that the first type was clear. How about the second type? The second type is endless, not repeating decimal are irrational. Okay, so let's just come and give some example for this one as well. Endless, not repeating. Endless, not repeating. How are we going to show this kind of numbers? For instance, if we have like 4.652 and there will be 3 dots here. So these 3 dots tell us that this number doesn't have an end. Okay, it's endless. And since no digit is repeating, so we are going to say that this decimal number is endless, not repeating decimal. And these type of numbers are irrational number. Alright? So according to these two types, non-perfect square root and non-perfect cube roots, and then endless, not repeating decimal are all irrational numbers. Perfect. So let's just move to the next note, whether we have it or not. So this is going to be very important. You need to take care of them. First thing is, the fraction with denominator 0 is not real number. For instance, we will later come to this one, but I want you to just shoot one example, 6 over 0. Since the denominator is 0, this is going to be non-real number. The first case is if we have got a fraction with denominator 0, so it's going to be non-real number. Perfect. And the second case is square root of negative number is also non-real number. For instance, square root of 4 is real. Okay? But square root of negative 4 is not going to be real. If the negative goes inside, so it's going to be non-real. But be careful, there are some cases, for example, something like this, negative of negative 4. So first of all, we know this kind of basic information that we multiply these two, then we will decide negative times negative is going to become positive square root of 4. So be careful, if there are two negative first, you need to multiply these signs to get rid of them and make it as a 1, then decide. If the final result was with negative, it's not real. But if the final result was with positive, so it's going to be real. I hope that it is clear, guys. And then in our second lesson, we talked about real number and estimating square roots. So, real numbers, as we already mentioned in the beginning of the lesson, real number consists of all those sets of numbers that we studied, but simply we can say that real number made up of rational number and irrational numbers. So they are going to make real number together. We can say that real number is equal to rational union irrational. So they are going to make a set, a universal set, which is called real number. So no matter the number is rational or irrational, it's going to be real. Perfect. How about non-real numbers? We already mentioned them. There are two types of non-real numbers: square root of negatives, as you can see, square root of -6, square root of -100. And then the second type of non-real number was number over 0, for instance, 2 over 0. These two types of numbers are non-real numbers. So here we can generalize like a real number set as in a Venn diagram. So rational number consists of this set of numbers. The smallest one is natural number, numbers like 1 and 10. The starting number is 1. Then we reached like whole numbers. They start from 0, so the difference between these two is just number 0. Then we reached integers. Integers are all the natural numbers, 0, and they're negative as well. For instance, -34 is out of this circle. And then finally, all these type of numbers are rational, like natural numbers, whole numbers, integers, decimals. So here is improper fractions like mixed number, proper fractions, repeating decimal, and we had terminating decimal as well, perfect square roots, perfect cube roots. How about irrational? So pi is the most famous irrational number, pi. Guys, whenever you see pi, it's going to be irrational. All right, why? Because up to this moment that I'm talking to you, there is no ending digit for pi. Therefore, pi is irrational. How about square root of 5? So square root of 5, it's imperfect. We already mentioned it. Negative square root of 7. Guys, I want you to know this one. The sign will not change the story of rational and irrational. No matter it is negative or positive, square root of 7 is irrational number. And then we have number line. Well, number line that you are already familiar with this mathematical term. It is a line that it has got two directions, left and right. So here, a number line is a line that there are like numbers on it. We numberize it. So we will show the middle of our number line with number 0. So it means 0 is located exactly at the middle of the line. So the right side of 0 would represent the positive numbers, positive integers, or positive decimals, positive fractions. So generally we can say that the right side will show the positive rational numbers. The left side will show negative rational numbers. Okay, as you can see here, we have got some examples. Not only for integers, we have got number lines for decimals, and we have got number line for fractions. So let me just give you some examples here. Or yes. So in case if I ask you or any other teacher or in any exam that you are taking it, if you saw a decimal number and said that represented on a number line, let's just say that, okay, if you have 0.61, okay, 0.61, you can just draw a number line like this, and you may just say that, okay, since it is let's say 0.6 and here is 0.7, because you must know that, at least you must know this point, that 0.61, it's between 0.6 and 0.7, all right? So imagine if you just go in order, 0.60 here, 0.70 here. So 0.61 would be here, then 62, 63, 64, 5, 6, 7, 8, 9, and 0.70. So the question asks us to plot 0.69 on this number line. So you are going to just circle it, and then the teacher would understand that This is 0.61 that you plotted on this number line. All right? Or simply, you can just turn it to fraction. So it depends on you whether you are more comfortable with decimal or fraction. Because, for example, for fraction, what if we have 6 over 7? And the question is, represent this fraction on the number line. So here is our number line. 6 over 7 is, let's say here is 0 and here is 1. Always for the proper fraction, so we have got 0 and 1. And based on the denominator, we will decide that how many parts should we divide this interval, this space on. All right? Divided into, I mean. So here, since it's 7, we have to divide this part, this interval, this distance between 0 and 1, into 7 equal parts. Let's say here 1, 2, 3, 4, 5, 6, and 7. So let's just numberize it. So here is 0.1, sorry, 1 over 7, 2 over 7, 3 over 7, 4 over 7, 5 over 7, 6 over 7, and 7 over 7, we show it as 1. Remember, 7 over 7, it's exactly 1. So if you want to just plot 6 over 7, I'm going to represent it on this number line. So we are going to say that, okay, 6 over 7 is exactly over here. So you can just mark it like this. That is 6 over 7. So when we have a fraction, the denominator will decide how many parts we have to divide that distance that we have by. So for example, here is 7, so we divide it by 7 equal parts, and we found the numerator parts. Okay, after number line, we have got estimating square roots. So for estimating, in grade 9, you already studied this kind of topics. Therefore, it's not going to be a big deal for you guys. Estimating square roots, we know that each imperfect square root is between two perfect square roots. For example, square root of 5, it's between 4 and, square root of 4 and square root of 9, which is basically, it's between 2 and 3. But which one is more closer? We are going to estimate it to that one. All right? For instance, here it says each square root, imperfect square root, is between two integers. To estimate it, we need to find out which perfect square root is closer to our root. We will estimate it to that one. For example, we have got square root of 34 here. Well, square root of 34, it's between square root of 25 and square root of 36. Okay, we have it here. 34, it's between two perfect squares. One is less, which is 25, and one is greater, which is 36. Okay, take square root for all these three numbers. We took it. Square root of 25, it's equal to 5. Square root of 34, we don't know it. We are going to estimate it to the nearest square root. And square root of 36, it's 6. But the distance from 36 to 34 is just two numbers. But then the distance between 25 to 34, it's 9 units. So which one is shorter, which one is smaller? We are going to estimate it to that one. All right? So since it's smaller, we are going to say that square root of 34 is going to be estimated to 6. As you can see here. Oops, let's just click on it. And the square root of 34 is going to be estimated to 6. Now we have got this question. Let me just... Okay, so I just wanted to make sure about something. I'm sorry, you guys. So estimate the value of square root of 28 and represent it on a number line. So estimate the value of 28. First of all, we must know that 28 is between two perfect squares. One of them is 25, the other one is 36. Now we need to take, square root for all these numbers, like square root of 25, square root of 28, square root of 36. Perfect. So square root of 25 is 5. Square root of 28, we are going to find it out which number we are going to estimate it to. So, and square root of 36 is 6. Let's just count the distance from each side to 28. So the distance from left side, which is from 25 to 28, is just 3. And the distance from between 28 and 36 is just, it's 80 numbers. So which one is shorter, which one is smaller? Absolutely from 25 to 28. Therefore, we are going to estimate it to 5. So finally, you are going to say that square root of 28 would be estimated to like 5. And finally, it says represented on the number line. So imagine if we have got this number line. So square root of 28, it's between 5 and 6. So here is 5 and here is 6. So approximately we are going to say that this is square root of 28. But since it's estimated to 5, it should be closer to 5. So we can say that, okay, here it can be square root of 28. It's more closer to 5. This is how we are going to estimate a square root and represent it on a number line. And then we have one more example, if I'm not mistaken. We have like square root of 77. We have our number line here. First of all, let's just estimate it. So square root of 77, it's between square root of 64. Guys, you must know the perfect square roots in order to make your job easier. Square root of 81. Okay. So the distance from 64 to 77, it's 13 numbers. So the distance, you can just check it. It's 13 numbers. And from 77 to 81, it's just 4. So which one is shorter? Of course, this one. Therefore, square root of 77, it's almost like estimated to 9. So it's between 8 and 9, and we will estimate it to 9 because it's more closer to 81. So here on our number line, we can say that, okay, here is 8 and here is 9. So square root of 77, since it was estimated to 9, so it's going to be somewhere around here. Square root of 77, it's more closer to 9 than 8. And I hope that this is clear to you guys. Then the next thing that we have is, okay, this is the homework slide for my students, so this is not much important for now, but if you solve these questions in page 20, that would be helpful to you. And then in our third part of our today's lesson, we will talk about properties shortly, because these are basic information and we must know them. So first property, by the way, we are going to talk about in two operation types. One is addition and one is multiplication. These two are the two major operations in mathematics. So addition and multiplication. And we have got 5 properties, 5 crucial properties that we need to take care of them. The first one is commutative property. Okay, in commutative, just guys, we are going to play with the place of the numbers. All right, which one comes first or which one comes second? Let's see whether it's gonna make any difference or not. Okay, let's just say that if A is 3, B is 2, and C is 4. Let's just imagine it like this. Okay, perfect. So for commutative, let's see whether it's satisfied for addition or not. So instead of A, we have 3. Instead of B, we have got 2. The question is that equal to 2 plus 3? Let's see. How are we going to realize it? If the left side and the right side were equal to each other. So 3 plus 2, 5. 2 plus 3, 5. Since left and right sides have got the same result, we are going to say that commutative property works for addition. How about for multiplication? Again, we have got 3 here times 2. Question is it equal to 2 times 3? Absolutely. 3 times 2, 6. 2 times 3, 6. So it means the commutative property satisfies multiplication as well. That was about commutative property, which is all about like playing with the place of the numbers. All right. How about associative or associative property? So we are dealing with three numbers. Again, let's just return to those numerical examples that we have. Instead of A, we have 3 plus. In our bracket, we have got 2 plus 4. 2 plus 4. And the question is that equal to A is 3, B is 2, and plus C. So basically, associative property said that if we add a number to a bracket, so this bracket can have like more than one number, is it equal to if we just change a number, the outside number with one like inside of the bracket, will it make any change or not? Let's see. So instead of this, we have got 4. Let's see whether these two sides are the same or not. So 2 plus 4, 6. 6 plus 3, 9. All right? The result of left side is equal to 9. How about the right side? Well, in the right side, we have 3 plus 2, 5. Plus 4, we got 9 again. So since left and right are the same, we are going to say that, we are going to claim that associative property works for addition. That's all about associative property regarding to addition. How about for multiplication? Again, we are dealing with three numbers. A number times a bracket. In our bracket, we have got multiplication of two numbers. Is this the same with if we change that outside number with one from the inside? So let's just analyze it. So 3 times, in our bracket, we have got 2 times 4. Is it the same with A is 3, B is 2, all times by 4. So first of all, 2 times 4, 8. 8 times 3, 24. Perfect. Is it the same with 3 times 2, 6. 6 times 4, again 24. Since left side and right side have the same result, we are going to say that, okay, associative property works for multiplication too. That's all about associative property. How about distributive property? According to its name, it's like we have to distribute something on something else. For example, imagine me, myself, the school just distributed me on the 4 grade 10 classes. So I will teach grade 10A, 10B, 10C, 10D. The school distributed me on these 4 classes for teaching them math. So right now, we will distribute a number on a bracket. So that bracket, it can take anything. We are going to distribute that number outside on inside the bracket. So for example, we have got A. Our A was, as much as I remember, it was 3 times. In our bracket, we have got B was 2, C was 4. Is it the same with if we distribute this one by each term inside the bracket? So A times B, instead of A and B, we have 3 times 2 plus 3 times 4. Let's see whether the left side and the right side are the same or not. So the left side is 2 plus 4, 6. 6 times 3, it's 18. So the left side is 18. If they were not equal, we are going to say that distributive property doesn't work for addition and multiplication. 3 times 2, 6. Plus 3 times 4, 12. So 6 plus 12, again we are going to have 18. Since the left and the right side are the same, we're going to claim that and concluded that distributive property works for addition and multiplication. Okay. During the solution, of a question, we are going to use this kind of properties. All right. In exercises that we have gathered at the end of this section, there are some questions that you can use this distributive property in order to solve them. Okay. And the last two properties that we have, they are very, very important. Identity properties. So for addition, identity means any number plus 0, it's equal to the same number. Or as a question, we can just say that, how are we going to add a number to something and get the same number? So this is only possible for adding to 0. Therefore, 0 is the identity number for addition. Because if you add any number, for example, 100, added to 0, it's equal to 100 itself. Negative 6, added to 0, it's equal to negative 6. Therefore, the identity number for addition is 0. How about the multiplication? Well, any number times what equals to the same number. So it's only possible for 1. Like, for example, 100 times 1, it's equal to 100. Negative 246 multiplied by 1, it's equal to negative 246. Therefore, the identity number for multiplication is 1. So the identity number for addition is 0. For multiplication, it is 1. And the last property that we have, it's inverse property. So inverse property for addition means a number plus its opposite is equal to 0. Okay? For example, 10 plus the opposite of 10. If we have instead of a 10 plus, what is the inverse of 10 in addition? So it's equal to negative 10. Positive 10 and negative 10, they will eliminate each other and the result is 0. And how about the inverse property for multiplication? For multiplication, a number, since we know that the inverse operation for multiplication is division, so we are going to conclude that a number times its inverse equals to 1 always. For example, let's just numerically take one example. Let's say if a is 2 over 3 times, what is the inverse of 2 over 3 in multiplication? We are going to take the reciprocal form or flip our fraction, so it's going to give us 3 over 2. Okay, so a number times its inverse, it's equal to 1. For addition, we have got a number plus its opposite, its inverse, it's going to give us 0. But for multiplication, a number times its inverse, it's equal to always 1. Don't forget about it. And then finally, in our last part of the first lesson in our book, we are going to deal with order of operations. Remember from the previous grade 6, 7, 8, 9, you are dealing with this title. And this year, order of operation is also a small part of the first lesson. Well, PEMDAS. PEMDAS is a code that most of the students actually use it. So P stands for parenthesis, E stands for exponent, M stands for multiplication, and D stands for division, A stands for addition, S stands for subtraction. But the question is, you might ask me, teacher, what if we have multiplication and division in one expression together? So then we are going to have sub rule, which is called, it says that if we have multiplication and division at the same time, since math starts from left to right, so we are going to count like this. Whatever comes first, either multiplication or division, we are going to deal with that one first. Okay? For instance, if you have got a let's say, let's just give one example. 2 divided by 1 multiplied by 6. Okay? So 2 divided by 1 multiplied by 6. First of all, from left to right, we have got division. So 2 divided by 1, 2. Then multiplication. 2 times 6, it's equal to 12. Okay? So from left to right, we are going to decide which one we need to deal with, either multiplication or division. For the addition and subtraction, we have got the same story, which is from left to right, whatever comes first, we will deal with that one first. So to find the value of an expression that includes different operations, we will follow this order, which is parenthesis, exponent, multiplication, division from left to right, addition and subtraction from left to right. There will be some other way, like in some books, some students got it as BEDMAS. So in that case, B stands for bracket, or Budmas. So O stand for order. In Cambridge system, they use these kind of words as well. So we have examples. Find the value of the given expression. 2 to the power of 3 times a bracket 1 plus 4 divided by 5. So as you can see, we have got power, parenthesis, and we have division. So first of all, we need to start from the bracket, which is parenthesis. Okay? So in our bracket, we have 1 plus 4. So 1 plus 4, 5. So let's just rearrange it again. 2 to the power of 3. In our bracket, we have got 5 divided by 5. We have exponent and division. Which one comes first? Exponent. Go back to PEMDAS. E. So 2 to the power of 3, 8. Times 5 divided by 5. 8 times 5, 40. Divided by 5, it's equal to 8. That is how you are going to deal with an order of operations question. Next question. Okay. Next question is very nice question. So we have got 78. So 78 minus. We have got a fraction. In our fraction, in our denominator, we have multiplication, a bracket. Inside our bracket, we have subtraction, addition, and then finally we have got exponent as well. Then we have got power in the denominator. So first, we have got bracket. So we have 10 times. In our bracket, 2 minus 13, negative 11. 2 minus 13, it's negative 11. Plus 1, negative 10. Negative 10 squared over 5 squared is equal to 25. Okay, so we have 78. Don't touch this 78. Minus negative 10 squared, it's equal to 100. 10 times 100 over 25. So there are two ways here. Either you can multiply this 10 by 100 and then divide it by 25, which is, I'm not going to suggest this way to you. Use simplification, simplify it. So easily you can say that 25 divided by itself, it's 1. 100 divided by 25, it's 4. So we have got 78 minus 10 times 4, 40. So 78 minus 40, I'm pretty sure guys, you know the result, which is 38. That was the end of the first lesson. I don't want to make it longer because I know listening to math videos are going to be like bored if they are long. So I hope that it was beneficial and you got a lot of benefit from it. My lovely students, see you in another video. Take care of yourself.